Okay. Good morning and welcome to the Grand Rounds for today. I'm Dr. Carrie Woodbury. We have our Chief Resident in Plastic Surgery, Dr. Mihail Climov, who's going to present Grand Rounds today. We're delighted that Mihail has been with us here in the plastic surgery residency program. He comes from Moldova and he has spent some extensive time in doing research at Harvard. And Mihail has been with us, a very active and a strong leader in the plastic surgery division. So today we'd like to say welcome and thank you, Mihail, for showing us a little bit of something that's special to you. Thank you.
Morning. Thank you very much, Dr. for such a kind introduction. And thank you all for coming, and especially for dressing up, for my round talk. It feels extra special. And also it's weird, but at the same time, very nice to talk about something, being here to talk about something that, of our choosing. So today I'm going to talk about something that I spent multiple years on, and just researching the bioengineered skin. So here's my disclosures. I'm a co-founder of Reduct Bio, and some of the work that I will be talking about was funded by Organogenesis through a grant to TBRC, NIH funding. I was on the T32, and also Harvard Stem Cell Institute funded a portion of this. So I'll give you a little bit of background, where I'm coming from, people I met through, before getting to WVU. So I was born in Moldova, which is a small country somewhere in Eastern Europe. It is landlocked. It is half the size of West Virginia, but double as populated. It borders with Ukraine on the north, east, and south, and on the west borders with Romania. It's a nice small country, but when I was born, it was part of the USSR. It's called the Moldovanian Soviet Socialist Republic, and also named the Blooming Garden of USSR. So it is known for wine production and in general with fruits and vegetables. And it was basically feeding the entire USSR back then. People actually lived very well in Moldova in the time of USSR, because the federal funding was dumping a lot of money to Moldova. It was the most Western country, so they need to show off that it's a good country. So people who lived in Moldova, they were actually very happy during that time. So after independence, the culture of wine was actually changed and evolved even more. Currently, there are more than 142 wineries in Moldova. So it is the 20th largest wine producer in the world. And it has the largest wine cellar in the world. It's called Mileshti Mici, it's somewhere in the center of the country. And it encompasses 120 miles of cellars, of tunnels, and only 30 to 40% of it is used. So Moldova is multicultural, multilingual culture. It is country. It is mostly composed 2/3 of Romanian descent, and shares the common cultural heritage with Romania. Romanian is the native language. There is some politics involved. So constitution, it's Moldovan language, which is basically, it is Romanian, but it's a dialect of Romanian if it, like we would call it here, American language, not English. So just recently, I think this year, in March, Parliament adopted that Romanian is the official language. So at the same time, Moldovans speak Russian very well. Many of them speak or understand Ukrainian. And also we have a good portion in the south, in the red area. People speak Gagauz, which is a Turkic language. So bordering with Ukraine, it's obviously multiple refugees transited through the country, over 1 million, I think. And a lot of them stayed in Moldova, over 100,000, which is about 2.6% of total population of Moldova. So after elementary school, I went to high school to Bucharest, and then I got a scholarship at this university, Carol de Vilan University. It is the oldest and largest university in Romania. One class is 600 people. So not everyone graduates. I think in my year, 554 graduated only. But it's a big university. It's over 25 hospitals, I think, and it's huge. So 6 years directly from high school. You are getting some admission testing before, and each university administers those tests. So you have to travel and take the tests, and sometimes they're not the same. Here, I think I took anatomy and chemistry. You have a choice of chemistry or physics. And then they pick the first 600, first 200 get scholarship. And I was one of 5 that got a special government scholarship. So couple of famous graduates from Karol Davila. Nikolai Pavlescu, I don't, probably you didn't hear about him, but he is the scientist who discovered insulin for the first time. He was a faculty, and he did the work while being at Karol Davila years before Canadian group was actually synthesized. There are publications in 1914, 1915 in French. Back then, the scientific world was speaking French, so but he wasn't recognized appropriately. So another famous graduate from Karol Davila was George Emil Palade. You probably have heard of ribosomes, right? So he's the guy, he's an American-Romanian scientist, and he discovered them, got a Nobel Prize for that too. So while in medical school, I was interested in microsurgery, and the only way to learn microsurgery was to get along with plastic surgeons. And this is my mentor and later became my friend, Dr. Dragos Zanfirescu. You have a lot of freedom in medical school, so many years. So all my free time I was spending with him, taking call with his team and staying overnight. So he encouraged me to do my dissertation paper on hemifacial transplantation in rats. It's one of my rats. We basically implemented the model that Maria Semyonov at Cleveland introduced. And it was fun and interesting. However, to follow the path of plastics, I decided only after I basically met with Dr. Fuchan Wei. He's a world-renowned microsurgeon from Taiwan. He started an extraordinary school there, known to the entire world. People from around the world are traveling for fellowships to learn microsurgery there. So only seeing that breadth and how complex it can be, I kind of started thinking about plastic surgery. And that's me. That's one of the courses that he ran in Bucharest. So after graduation, I did 1 year of internship back in Romania, and having the microsurgical experience, also interested in research. I landed a job at Mass General Hospital for a year in a stroke lab where I basically did microsurgery on mouse brains for a year. It wasn't that exciting, but it was very productive here. So in a year, I moved from the 6th floor of the same building to the 9th, and I joined the TBRC Transplantation Biology Research Center, which is an extraordinary place to train in research, led and founded by Dr. David Sachs. And I took charge of this project, and I will talk about this a little later. So David Sachs is centered there. So he was the mastermind behind the successful transplants. So basically kidney transplants that you perform special conditioning, and then you don't need immunosuppression after that. So first publication, 4 out of 5, tolerant kidneys for 5 years. Second one, 50% success with that specific regimen. So it's the way you basically are making a chimera. It's hematopoietic chimerism induction. And this way the body tolerates the new organ. He also discovered the MHC class 2 and received Medawar Prize for that, which is equivalent of a Nobel Prize, but in transplant world. So my PI, Christine Hong, Dr. Sachs, one of our illustrations from our publication ended up on the cover of Transplantation. So in 2013, there were budget cuts in NIH, so I lost my T32, and I had to do some Uber, Lyft driving. So until I found Dr. Orgel, and I moved to the dark side. So MGH and Brigham, they are rivals. So I moved to Brigham, and I got to know Dr. Orgel. Dr. Orgel, for those of you who don't know him, he was the PhD student with Dr. Berg and Yanas, people who developed Integra, I'll talk about later. But he was doing all the transplants and experiments in the 80s, early 80s. So he had a major interest in skin. So it was a very natural and benefic transition for me. Also, one of our illustration ended up on the cover. So during this research years, almost 7-year saga, I was fortunate to meet these two great surgeons that kept me sane and in contact with clinical world and inspired me and our friends, and we still talk and discuss the path for the future. So Dr. Elof Eriksson on the left, he was the chief at Brigham Women's Hospital for close to 30 years. He was the chief after Joe Murray, the plastic surgeon who got the Nobel Prize for kidney transplant, so big shoes to fill. And Dr. Pribas, just an extraordinary plastic surgeon, reconstructive surgeon. He probably is the only one that I personally know that could reconstruct a face, complete face, with traditional methods, flaps, multiple serial reconstruction, that would look like a face at the end. So amazing. Currently he's an interim division chief at Tampa, and he's retiring June 30th. And finally, I managed to WVU. So much excitement. So it's been very interesting and productive professionally, 6 years. But also personally, this is my support team. We've got 2 new members on the right. So now taking to the subject of this presentation, bioengineered skin. So although skin is, as we all know, it's the largest organ of the body. And apparently it's simple, right? Just 2 layers, but it does so many things and it's very complex. So till now, we do not really understand how it does the function that it does. So the first line of defense, right? It protects us against physical, chemical, but also biological, right, trauma. But at the same time, it constantly samples the antigen from outside and responds adequately. So it is a self-controlled bacterial incubator to maintain our flora. So, and also it has twice the number of T cells than you can find in the blood, which makes it very highly immunologically active. There are multiple situations when you have loss of skin, especially large burns, right, or excisions. And usually the treatment of skin grafts, but there are situations when there's not enough skin grafts. So alternatives are needed. So we went, humanity in general went a long way from using just the cotton and honey for the wounds till we got to the bioengineered skin that we have currently available. But important milestones, I think, were the skin grafting technique, narrowing down how it was done, and also Medowar's experiments in the 50s, where he showed that allograft or allogenic skin can actually get tolerant or be immunoprivileged, also with induction of chimerism. So the general term for skin, bioengineered skin, is skin substitutes, and that's what you will see in the insurances. And however, it's a misnomer because not everything is actually does substitute the skin. So most of them act as biologic dressing. So just something to keep in mind. You may not know, but the origins of skin engineering were in Boston area in the 70s when with advance of ICU, critical care, so the patients who usually died before severely burned patients, they started living longer. So there were no alternatives to how to cover that. So NIH started funding aggressively, and there are several groups in Boston area that focused on the different directions to replace the skin. So one of them focused on epidermis, another group thought that dermis is more important, and the third that we need to replace both of them. So the group that focused on epidermis was led by accident by Howard Green. They were working on sarcoma cells in 1975, and by accident found the way to culture keratinocytes that was not possible before. So So basically, if you take murine mouse fibroblasts, you irradiate them, and you seed keratinocytes on top, they will start growing. It provides the nutrients that are necessary. So this way, you can actually culture an epidermal sheet, 5 to 7 cell layers thick, that you can transplant. So that led to a new product, and currently it was called Epicell, or cultured epithelial autografts. And it was tested in the 1981 initially, then 84, also at Brigham. So it is usually reserved for severe burns that are over 50% total body surface area. Then this is not covered by insurance. It's very expensive. It's patient specific. You take a biopsy, then you expand those cells, you create sheets, but you can create a football field of skin for the patient. So usually in hospitals like Shriners, there are special funds for this. The problem, it doesn't have the dermal component, so it's very fragile. It's and engraftment, that's why engraftment rate is pretty low too, compared to a skin graft. So another group focused on the dermis. So it was Dr. Ioannis Yanas, who was a professor of material science at MIT, and John Burke, he was the chief of staff at Mass General Hospital and also at Shriners. So they were thinking to create something cheap, easy, made out of regular elements that would get the patients through the initial phase of the burn, and then you can deal with it later. And so Dr. Yanas came up with this formulation using bovine collagen and shark glucosaminoglycan chondroitin 6 sulfate. And so they mix it together. Dr. Burke didn't believe that epidermis is important, so that's why Integra has a silicone layer on it. There's a story behind that also. He hated epidermis because when he was in training, he was sort of forced by his mentors to do epidermal grafts on roosters' combs. So he really, that's why Integra probably is what it is right now. So basically, they created a library of different scaffolds and different formulations with different pores and different cross-linking. And then they put it on animals and they followed which one engrafts, and to find, basically empirically, to find the best combination. Only 20 years after, when they started looking why Integra works, why they found, specific dimension of the pores, I think 120, and the cross-linking should be of specific degree. But they empirically found a scaffold that you can put on any full thickness wound or partial thickness wound, and vessels would engraft through it, and it will form something that resembles, it's a non-contractile scar, but they called it as a regenerated dermis, and there was nothing available. So initially they were actually afraid to publish it because instead of healing the wound quicker, that was the hope, it would last for 2 or 3 weeks. That's how long it takes for Integra to engraft, usually 3 weeks. If you use a negative pressure wound therapy, then it will take 2 weeks, so decreasing that. Also, it is cheaper than the previous one, the Epicell, but this is the price, how much Medicare reimburses, but it's not the actual price. It's usually, they say $15 to $30 per square centimeter. So the advantage is slow regeneration and will require a skin graft if it's a big area. For small areas, it will epithelialize later. So there are some alternatives developed in I think, Japan some time ago, and the Pelnac and Dermis, but they will never get FDA approved because they're basically copies of Integra. So another group later, like 10 years or 15 years, thought, why bothering creating a scaffold? Let's just take cadaver skin and just decellularize it, and we'll have a scaffold. So method is good. This how alloderm, another extracellular matrix derived construct was developed, and many others. You can use the same method of decellularizing. And initially it was used or tested as a burns treatment, skin substitute. However, it wasn't as efficient, but still you can use it. And now it's mostly used for in breast reconstruction as a sling. So you can apply similar method of decellularizing to any tissue possible, but there are multiple brands, multiple variation. to different even origins. So you can do a fish skin. The problem is that not everything will engraft. So not every product. So you need to know which one, which is specific. So the third group focused on developing both layers, and Eugene Bell was the driving force. He basically was playing with fibroblast and collagen. He was putting them together, and the collagen would, the fibroblast would start remodeling your collagen, and that's how. And then you would seed keratinocytes on top, let them stratify, cornify, and you would have something that looks like skin. And an initial publication in Science in 1981, they were so excited, and they were saying that it's actually engrafts, and it does not reject across immunological barrier, which was not true. So later on, it was shown that basically this type of scaffold does not get penetrated by the vessels, and that's why it stays. It looks like stays, but doesn't reject actively. So the only clinical application for this product was Aptegraph, which was a very expensive biological dressing for chronic wounds. Efficient, but very expensive. There are several similar products. One of them is autologous. So that company did not get an FDA approval. They had in their clinical study, someone died, so it was complicated. And Stratograft is the new version. It uses the similar approach, but it uses different types of fibroblasts, and apparently it somehow stays or persists longer, kind of avoids the immune response. So at the time when I reviewed all the skin substitutes, I found over 172 products listed. However, medically necessary one is 7, and 2 of them just didn't make it. They got bankrupt. And that's another interesting question, why successfully or interesting scientific products, they don't really make it on the market. So basically, yeah, the ultimate goal is to have an off-the-shelf product, right, that will provide the permanent coverage and will induce a minimal donor site morbidity. So here comes our research with organogenesis. So again, just to remind you, this is a cross-section from a construct, skin construct that is done by Aptegraph method, basically fibroblasts and collagen. You let them remodel, and then you seed keratinocytes. And on the bottom, so fibroblasts, if you grow them with vitamin C medium, they start making their own extracellular matrix. So that's what this is. It's a the method is called self-assembly. So below, it's a new type of bioengineered skin where fibroblast made its own extracellular matrix. And then you do the same, you seed keratinocytes, let it stratify, cornify. So the idea that we know that skin is the most immunogenic organ, we don't know why, right? So the idea is that we basically develop a construct right now that it doesn't have any antigen presenting cells. So no dendritic cells, nothing that actively presents. So the hope was that by simplifying the structure, we will have something that will stay longer. So transplant biology is really complicated. Just to dilute it and to just make it simple for you, you have MHC class 1, it's on every cell that has a nuclei, right? It marks the self. MHC class 2, only on antigen presenting cells. It presents the antigen, shows to the body, this is the antigen, we need to attack it. And there are minor histocompatibility antigens, minors. So it's basically any antigen on the surface that configure immune response. So in order for a skin or anything to be accepted, you need to match in all 3 of this. So MGH and now Colombia have this miniature swine that has, by inbreeding, it has a very specific characterized MHC class 1 or class 2. So it allows you to do all these transplants in between with the known exact MHC. So the worst case scenario that's technically impossible in nature is a full mismatch when both MHC class 1 and MHC class 2 mismatches. So that's why we took DD animals as donors and CC as recipients, so a full mismatch situation. We took biopsies from donor animals when they were neonates, small pigs. Then we banked the cells and we started generating the construct. It takes around 6 weeks to do that. And then subsequently we proceeded with grafting. And on 5 animals, we grafted it in 5 animals. This is just a control. You take a skin graft from a full mismatched animal, you put it on the donor animal, on this recipient animal, and you can see rejection. It already started at day 4. At day 6, skin graft is literally destroyed. All right, so we proceeded with grafting, pretty simple. We grafted the construct. We did 2 constructs on the same animal, and then sham control and an autologous skin graft. Then we would do a dressing change on day 4, 6, 8, 10, 12, and we would take pictures and take biopsies as well. So unfortunately, it also rejected. So, but initially on day 4, it showed, you can see little vessels coming into the construct. So looking beautiful, healthy. By day 6, you see perivascular infiltrate, and these are T cells there. So it's basically getting attacked. And by day 6, it just sloughs off, leaving completely naked wound bed. Disappointing. So then we tested serum for the same animals, and animals developed after 2 weeks anti-MHC antibodies, and this test shows that these antibodies were actually cytotoxic. Good thing, we saw some engraftment, which is really great, but it rejected and there are antibodies there. So we proceeded with the second grafting in 7 weeks from that. So we grafted the same construct, and we also grafted a construct that matched with the MHC. So it was a CC. So the only mismatch would be the minors. And the expectation was that if you take the same construct, it will reject full mismatch construct, it will reject much quicker. And if you the other construct with minor mismatch, that should last a little longer. It will be a first set rejection, but with minors, it's usually a kind of a longer rejection. Unfortunately, they rejected by day 4, both of them. Very disappointing. So we were thinking, what's going on? Why? What happened? So we thought maybe the while growing, culturing, we incorporated some antigen into this skin. Or another option would be that the animals were presensitized to the minors during first rejection, or the construct, because they do not have other types of cells, may not have the cells that normally modulate the immune response. So we went back to the farm and we looked for the animal that donated initially the neonate skin. So we luckily found it. We generated our skin and we engrafted it. So it engrafted beautifully. It looked like its own skin. So this is a comparison: split thickness skin graft and autologous construct. So you would see engraftment, vessels are forming, and that's kind of the late. We followed the animal up to a year. So it looks like a beautiful skin with retiridges. The only difference is you can see the collagen fibers are more vertically oriented. And they're a little bit, the vascular plexus is different. So this resembles more of a scar, but otherwise looks great. So what we think happened, because it got vascularized, antigen presentation occurred, that activated the T cell response, and cytotoxic T cells destroyed the construct. So in summary, all the allogeneic constructs, unfortunately, rejected, but they engrafted, and the autologous one could be an interesting product for the future. So, however, back then, organogenesis, there were some changes in funding. FDA changed some definitions, and organogenesis basically fired the CEO, fired the entire research department, and we lost the funding for this project to pursue other directions. So, but we got back later, and that's how Reduct Bio started. So what are the potential strategies to achieve immunoprivileged skin? So one of them is to just add into the construct some cells or cytokines that can modulate the immune response, or use technologies like CRISPR to modify genetically allogeneic tissue, or potentially the host, modify some things in the host. So I transitioned to Dr. Orgil's lab, and we focused on some of the aspects, and I'll not talk about all of it, but I'll talk about something that I think is interesting. So we partnered with the Center for Integration of Science and Industry from Bethel University with Dr. Ledley. He had a Nature publication, Nature Biotechnology, and basically, for biotechnology, there is no way to predict performance. So in computer world, it's pretty simple, right? Processing power, that's your performance. So every couple of years, you see a new core added to your processors, right? And that's how you have this technological jump. So any technology evolution can be depicted as an S-curve. And you have an innovation. That's what the papers or where the initial experiments were conducted. Then you have maturations or progressive increase when all the kinks of the technology are sort of fixed and productivity is getting to the maximum, and then it achieves maturity. So you can, it's a model, you apply this model, and you can basically gauge how the technology perform, what is the stage of technology, does it need a new technological jump? So we were curious why some constructs are successful, some products are successful, and some are not. So that's why we went into this. So the genius of Dr. Ledley is that he found for biotechnology a good surrogate of performance papers, articles, scientific articles, which every article is basically a source of light. And if you quantify all of them, you can actually modulate and look at the trends that this technology presents. Also, number of patents and the products for that technology. So we applied the model to bioengineered skin. Basically, there's so many technologies. So we separated them in 3 different clusters. Process biologics, which would be cadaver skin, or extracellular matrix technologies, which would be alloderm, right, of the extracellular matrix technologies, or cell-based technologies, everything that has cultured cells in it. So we modeled, we looked at the papers, and not surprising, we found the technology establishment for process biologic in 1992. So basically right now, it's kind of going into senescence and potentially obsolescence of the technology. There's nothing new with the way of we preserve cadaver skin, right? We can just freeze it, or we can burn it, radiate it. So that's the only, no other things. For extracellular matrix technology, so Integra, alloderm, the peak was in 2010. So which means that there is nothing new as well for the last 13 years going on. However, the cell-based technologies, they're still in mature growth. So they're still in linear growth. So this is it tells to me that this is the area to invest your time and to focus. Probably that would be the future. So we also looked at the number of products that came from this cluster of technology. And extracellular matrix technology was the most successful and productive. Probably easier regulation, and in general, easier to make and manage than cell. So just wanted to throw there are a couple of predictions that which didn't turn true, but still it's encouraging, and it looks like the financial world is looking at this, expect this global market to really grow in regenerative medicine. And this is just how much funding was given to regenerative medicine in this is 2020, 10.7 billion, and in 2022, 12.6 billion. The problem was COVID that kind of decreased the amount of funding and trust in these technologies. So here comes since we were not supported by organogenesis anymore, we didn't have funding. So we decided to come together, all the people who were invested in this. We started a company. We found an angel investor, and basically the idea was simple. We also got Luhan Yang. She's the one of the original inventors of CRISPR. So basically the thought was simple. We take the same model and we apply initially in pigs. We just apply CRISPR and we edit genetically those tissues. And then we create our constructs and just do a proof of concept. So it's still ongoing, still lots of work to do. So in summary, despite the significant technological progress, unfortunately, there is no really a real skin substitute yet. And interestingly, the first in concept products are still on the market and are well used. So I would expect to see an increase in the usage of living cell therapies in the future. And probably the allogeneic modality has the most potential success to be off the shelf due to its off the shelf advantage. So multiple people, multiple sources to thank. And thank you for your attention. Happy to answer any questions.
Share with us about our use of Integra and what we can expect in terms of the best outcome for patients.
So personally, I think the way, so initially Dr. Burke and Yanas, they didn't design this as a very fancy product. It should have been easy and cheap and everyone should use it instead of skin. So I think this is a big problem and I don't like how Integra Life Sciences is kind of managing it. It shouldn't be a 20,000 piece of Integra. So however, it's a great product. I think especially it is useful in population that we have here that, are underinsured, live far away. You cannot admit them for a long time, or they are smokers, they have other comorbidities where, creating another defect, especially if you need a bigger piece of skin to harvest the skin graft, it's just safer to put something, off the shelf, and it will temporize, it will control the wound initially. And also Integra is designed, if you wait enough, it will actually epidermalize as well. So I think it's a great product. It's something to consider in many cases, but the wound has to be clean. It has to be debrided appropriately. It has to be, so Integra should be treated as a skin graft. So if you wouldn't put a skin graft, you should not use Integra. So Integra comes in different flavors as well. So there is a bilayered dermal matrix, I think. Yeah. So this is a bilayered wound matrix. That's what you want to use. We also have available Integra Thin, which is basically Integra without the silicone layer. You can put it under the skin. And unfortunately, we have a couple of instances that we open it. And it's an expensive piece that we should avoid using unless we're certain that we're using it for the situation. No. Oh, there are multiple available. So there are multiple available. So Epicel, Vericel, available, very expensive, right? Only in Shriners Hospital, insurance doesn't cover. Take a biopsy, you culture, but it's just epidermis. And lately, some reports showing there are cancers occurring later on after that. So you can use Integra. You can use pale nectar dermis. It's not available here. There's another product called Metriderm, which has more, it's like Integra, but has elastin fibers. They are incorporated. Some say it's better on the hands in general. There is Stratagraft. It's a very interesting product. It's made out of allogenic stuff, different types of nicks, and they keep it as a secret how come an allogenic product does not get rejected. And I'm personally interested. I looked in the papers. Why? Is that they probably confuse the immune system. So they mix different types of MHC, and they're a little bit attenuated. They use this, long Nix cultures. They're like keratinocytes that are growing in the lab for years, so they lose a little bit of their properties in general. So there are multiple available, but not everything is medically necessary, which means if it's not medically necessary, insurance will not pay for it. Or depends on the hospital. You might find some of this, depends on the contracts between hospitals. You can use different variation of it. So it's still underused resource, I think. But I think the main problem is how they manage the finances. It shouldn't be expensive. And that should be the goal. Not making it something like, oh yeah, this Integra. No, this is like a dressing. That's how it should be marketed, and that's how it should be priced as well. Good, thank you. Just delete my stuff.
It will delete once we get off.
Oh, okay. What did I do?